A couple of videos ago, we proved the convex function inequality. We did it like this. We took a convex function f of x, convex up, and we took a point S, the midpoint, a plus b over 2. And from x1 to x2, this is our region or domain of convexity where we're sure that f of x is convex. And we take this point G, and from this we derived an interesting inequality. We noticed that SP here, let's highlight this, SP is less than SG, always less than or equal to. And from this we get the convex function inequality, which has many very interesting implications. Now, if you want to see me derive this, I'll leave the link to that video in the description box. Now, there's nothing forcing us to take the midpoint, a plus b over 2. We could take some other point. For example, we can take this point G here. Now we're not at the midpoint, we're somewhere else. And this might give us some other kind of inequality. And yeah, it does. It gives us Jensen's inequality. So what's the right approach here? Well, the right approach is to determine this point G. And how do we determine this point G? Well, we have two weights, P1 and P2 here, weights of these points. And let's say here, in this case, P2 is heavier. So this length is going to be proportional to P2, and this length here proportional to P1. Okay, so it's G, the fulcrum, the point of balance, is closer to F of B here. And likewise here, if we project downwards, we'll get the same phenomenon. This is going to be proportional to P2, and this will be proportional to P1 here, sorry, P1 and P2 here. It's very easy to mix these things up. So I hope I don't do it again. So how do we find this point G here? Well, we use division of segments. And if you're not familiar with this technique, I've talked about it in a couple of videos. I will leave the links in the description box, but many of you are familiar with it, so you'll be able to follow everything going on in this video. Okay, so G is going to be P1 V1, and V1, what is V1? V1 is A F of A, like that. And V2, point vertex, this is going to be like my vertices. V2 is B and F of B, like that. Okay, so that's P1 V1 plus P2 V2 over P1 plus P2. Notice that P1 is lighter, the weight is less at V1 here, and the weight is heavier here, so my fulcrum point G is closer to V2. I talked about that in the previous video. It will help to set a kind of intuition for division of segments, so you won't make that mistake that I did here with P1 and P2 mixed up. That's a very instructive mistake. That can happen at any time. You know, if you're not paying 100% attention, like I wasn't for a second there, and I mixed it up. So don't let that happen to you. Watch that video and try to get the intuitive feel for why the P1, this segment is proportional to P1 here, and this segment is proportional to P2. Okay, now let's get some space here. I think I want that diagram again. So again, let's keep in mind that V1 is A F of A, and V2 is B F of B. So if I project downwards onto the x-axis, I see that the g of x, the x component of g, is the same as the x component of s. And so this is going to mean that s equals P1 A plus P2B over P1 plus P2, like so. Okay, and the y component, well, we can determine that from here. We can get the y component of P and G if we need it. So the convex up function f of x will have this property that this length here is always less than this length here. Okay, so let's try to write that down. SP is less than or equal to SG, like so. And so what is SP? Well, SP is the, this is the x component of S. Well, we just apply the function. SP, this length here is just f of SX, like this. So SP is f of SX, and that's f of P1A plus P2B over P1 plus P2. Okay, and what is SG? Well, that's the y component. The length from here to here is the y component of G. And what is the y component of G? Well, we can work it out from this expression here, from this, and we know this. So we plug these two into this one here, and we take the y component, gy, and we get this. P1 f of A plus P2 f of B over P1 plus P2. And combining these things, because we know this is the convexity condition, this follows from convexity. So we have this beautiful inequality, P1A plus P2B over P1 plus P2 less than or equal to P1F A. Let's see if I can fit this in. P2F of B over P1 plus P2. Very beautiful. Let's put a box around that. This is actually Jensen's inequality, but there's usually a kind of little thing that we do. Well, I'll show you right now to make it a little bit more elegant. So what I'm going to do is normalize the weights. Right now, P1 and P2, they're anything. I mean, I can choose, for example, a proportion here of 5, and this is 2. So it's 5 to 2. Okay, so yeah, I can choose anything. I can choose proportion of 7 to 3 or whatever, anything. So these two numbers can be anything. But if I normalize them, then things become more elegant. So I choose a change of variable. So I'll choose Q1 is P1 over P1 plus P2, and Q2 is P2 over P1 plus P2. So now I have this beautiful property that Q1 plus Q2 is 1. Okay, so that's very nice. And if you look carefully here, let's use color. This is, well, that's not a good color because I already used that color. Okay, this is Q1, and here we have Q2. So, okay, we can rewrite everything. So if I choose Q1 and Q2 so that they add up to 1, I now get f of Q1A plus Q2B is less than or equal to Q1FA plus Q1FA plus Q2FB. There we go. And that is Jensen's inequality, and with the condition that Q1 plus Q2 is 1. So this is our friend Jensen. So it's it's like the convex function inequality, except it's been Jensenized, it's generalized or Jensenized to different weights. And this is for a convex up function f. If you don't know what I mean by convex up, you've got to watch the video that I'll put in the description box. All right, so let's see some applications of Jensen's beautiful inequality. Let's do some examples, some applications and implications of Jensen. Let's take f of x as x squared. That's a convex function on the domain. Okay, so domain can be anywhere x1 less than x2, with x1 and x2 could simply be anywhere on the real line, and this function is convex everywhere. So write down Jensen's inequality. F of q1a plus q2b is less than or equal to this combination, where q1 plus q2 is equal to 1, and of course a and b, a is less than b or less than or equal to b, and they're inside this, I'll take it like that, inside this domain of convexity. Okay, so what do we get when we plug all this in? We get this, take the square root of both sides, and we have this. This is a Jensenized version of RMS, root mean squared. And you say, well, I don't really see it, you know, it doesn't look like, this doesn't look like RMS or arithmetic mean. Well, it is. It is because, okay, so we'll take Q1 is 1/2 and Q2 is 1/2. These two add up to 1, so that's a legal choice. And if we put those two in for Q, we get A plus B over 2 is less than or equal to 1/2 A squared plus B squared over 2. And this is actually RMS. That's the usual one, you see. But the Jensenized version is more powerful. We have weights that we can attach to A and B. It gives us a lot more flexibility. Look at the form of it when I put back Q1 is P1 over P1 plus P2, and Q2 is P2 over P1 plus P2. Let's see what it looks like. Now the form is more recognizable. You see that what we have here, this is like generalized arithmetic mean, and this is generalized RMS or Jensenized RMS. So it's an amazing result. Like it still works even when we put weights on these points. We get a more general version. Very amazing. Okay, let's try another example. F of x is 1 over x. Well, if I take x1 greater than 0 and x2 greater than x1, and I form my domain, then all the points in this domain are convex. So this is a convex domain, and I choose A and B inside, and no problem. I have Jensen's inequality applying to this function now. So here's my Jensen inequality. Like usual, it's best to write it down first and then see where everything goes. Now we'll plug in this function here, 1 over x, and see what happens. We get this, and let's try to rearrange things a little bit. There, I brought this one to the other side and so on. Okay, and so what we have here is Jensenized harmonic mean, and this one here, up here, this is Jensenized arithmetic mean. And you say, well, it doesn't look like it. But if I put back these two, it becomes a lot clearer. Let's see. Now it looks a lot like harmonic mean and arithmetic mean. So if I take P1 as 1 and P2 is 1, they're not normalized, but now I'm okay. I'm not using normalized weights anymore. If I take these two, I get back exactly the HM. Let's spell this right. HM inequality. I get it back. But I got plenty more inequalities just by plugging in P1 and P2 being anything I want. Okay, so it's very beautiful. What a beautiful derivation of the Jensenized version of HM. So let's do one more. And this is going to be the big one, my favorite one, minus log x. Minus log x is convex up. You can prove that by taking the second derivative, but we need to have x1 greater than 0, of course. And then so on, then we choose a less than or equal to b, and all of these things less than some x2, which is larger than x1. Okay, and we're in the domain of convexity, so everything's convex. Start with Jensen's inequality and our normalized weights here, okay? Because it's more elegant to do these calculations this way. Now plug in minus log x. We get this. Now, if we're going to get rid of the negative signs, we have to flip the inequality around. And we get that. Now, this part can be combined very nicely like this. Watch. Log a q power of q1 plus log b power of q2 less than or equal to the same thing. And these logs here can be combined also to get log a q1 b q2 less than or equal to log q1 a plus q2b. And where does this go? Let's see. Get rid of the logs, and I have a q1. Let's write this bigger. A q1 b q2 less than or equal to q1a plus q2b. What an amazing formula with, remember, q1 plus q2 is 1. This is generalized or Jensenized MGM. Because if I choose q1 is 1/2 and q2 is 1/2, well, okay, if I do that, then they add up to 1, so that's a legal choice. And if I do that, I get a power 1/2, b power 1/2 less than or equal to a plus b over 2. And this is root ab. I'm sure you know this. And this is MGM. It's beautiful how we get MGM as a consequence of Jensen's inequality. In fact, let's put back these unweighted ones. Sorry, not unweighted. I mean unnormalized weights. That's dyslexia, Okay, so let's put that back into this formula, and we'll see it's very interesting. So we get this. Very beautiful. This is our generalized, Jensenized version of MGM. I think this is a really beautiful and totally not obvious formula or inequality, and I'm just struck by this. Let's write beautiful over here. Okay, so as an exercise for you, before we move on to the last part, as an exercise for you to do, take this function, x of p, where p is greater than 2. Okay, this is going to be convex on the domain where x1 is greater than 0. And what do you get? What do you get? You're going to get some kind of generalized version of some inequality we may have seen before, but you do the calculations. And if you want, you can write about it in the comments. Up until now, we have been proving baby versions of inequalities. Let me show you what I mean. See, all three of these famous inequalities, the way we have written them, they only involve two numbers. So that's really simple. In fact, it's so simple. These three can be proved by algebra methods, you know, by looking at polynomial and something like that. It's really easy to prove them. However, here on the right hand side, I now have many quantities. I have A1, A2, and so on up to AK. So it's like K-way inequalities, or as I set it up here, N-way inequalities. And these are much harder to prove. Much harder. And as an example, I did some videos a while back, 2 videos where I proved this one by means of algebra. I used induction, and you can see from those videos that it's not easy to prove. It's technical, and it took 2 videos to do. However, in this part of the video, I'll prove all 3 of these. Well, actually, I'm going to prove this one, and you are going to easily prove these 2, because it all follows now from the N-way Jensen's inequality, and one more thing which is needed. So we need the N-way Jensen inequality, and one more really magic thing. I'll tell you what it is. We will need this, the convex polygon centroid theorem. That I did in the last video. I will leave a link to this also. I'll leave links to all of these things, all of these videos in the description box. However, in that last video, I said this is a very, very powerful theorem. Without this theorem, you wouldn't have linear optimization, you wouldn't have statistics, you wouldn't have machine learning, you wouldn't have any of those nice things. You wouldn't have any of these theories of inequalities. All of it would fail. You need this theorem. It's super powerful. And we will now use it, and I will prove to you, I will convince you that this is a very, very powerful theorem, because it will allow us to easily deduce all of these inequalities. And it'll allow us to easily deduce N-way Jensen, and then everything else just follows automatically from this. So this is a super powerful theorem. And to refresh your memory, the theorem is like this. Let's say pi is a convex polygon with vertices, vertices v1, v2, vk. So it's got k vertices. So we form the weighted mean of these k vertices, call it g, and g is always inside pi. It's never outside. If the polygon is not convex, it can be outside. All of this analysis failed. That's why convexity is really important. It has this amazing property, and this is the key property to proving the most powerful version of Jensen's inequality, which is the N-way one. Okay, so let's get to work on that. I need my figure now. Here's my figure, and let's take stock of this. Let's have a careful look at what is going on here. So I have my domain of convexity, x1 to x2, okay, with x1 less than x2. I have guaranteed that the function is convex on this domain, and I choose some points. Let's say I choose k of them. Well, in this case, k is 6, less than or equal to a2, 3, and so on, less than or equal to ak. In our case, I chose k6. That's about as many as I can draw and still have a clear diagram. Okay, and I have vertices, v1, v2. Okay, so v1 V1 is point A1, f of A1. Okay, so it's A1, this is the x coordinate, then I go up, and that's f of A1, that's the y coordinate, and in general, Vj is Aj, f of Aj. Okay, so it's important to be clear about that because this helps us derive everything. And notice that V1, V2, up to Vk, in our case Vk is 6, this is our polygon, this is pi, our polygon pi. Okay, so I will shade it in and then erase the shading because I don't want to screw up my diagram, but you can see it's clear, and you can see the polygon sides here. It's clear for some of these. They're all straight lines. It's clear, and this one is not clear because the straight line is very close to the curve f. So okay, it's not so clear, but you know, it's right. It's there. You know, this is a polygon. And not only is it a polygon, but pi is convex. Why is pi convex? Because f is convex. Okay, so I'm taking sides constructed along this convex curve, so of course it's a convex polygon. And so therefore, by our favorite theorem, therefore by the convex polygon theorem, the convex poly theorem, G is inside polygon pi, and this makes all the difference. If G was outside polygon pi, then Jensen's inequality would not work in this case. Right? I'm sure you can see that, you know. It has to be below this line. G has to be below this line. Otherwise, it won't work. Okay? Well, actually, okay, if G is above this line, it'll work. It'll work. But if G's below this line, yeah, then it won't work at all. Then Jensen's inequality won't work. But you'll probably have some pathological behavior if G is above this line too. You know, because we can derive a different inequality using this line from f of a1 to f of a6, and it will contradict that. This has to be below this point, less than or equal to this point. So something's going to go wrong if G's above, and Jensen's inequality is going to go wrong if G's below. That's for sure. That's for sure. Okay, so let's see what can we derive now? Well, we can see that this is going to be less than this. So SP, like usual, less than or equal to G. Okay, you see, okay, if G goes out up here, that's still true, but other things will happen. Other contradictions will happen later on. But if G is below, then this is no longer true. Okay, that should be SG. Okay, so we absolutely need this theorem. We must keep G inside the polygon. And luckily, because polygon is convex, then it's always true. Okay, so let's write that down. So SP less than or equal to SG. With G is this combination with weights. I attach weights to these points. So P1 is the weight of V1, and P2 here, and P3 here, and P4, and so on until PK here. As you can see, the weights of these points 5 and 6 are heavier than the others, so that pulls G in this direction. Okay, so I chose weights, pretty simple ones, 1, 2, 3, 4, 5, 6, like that. And so you can duplicate this figure if you really wanted to. Okay, so the x projection. Now we project g down to the x-axis, and we see that the x component of g has got to be the same as the x component of this point S. Same reasoning like before. And we can then get the x component of S from this. We just plug in, as we did before, this. Put these vectors, points, into this formula and take the x part, and we have the x part of S. So that's easy to find. And so from this, it's easy now to determine SP. Well, let's go back to the picture. What is SP? That's, if I know SX here, that's the x component. Well, this length from here to here, that's f of Sx. It's just the y component of p is py. Okay, so that's easy to reason about. So I can now do this. And it's just the function f applied to that point. Okay, so now we need SG. So let's erase some of this stuff. And now I need this length here from S, from the x-axis up to point G. So this is actually GY. So this is the y component of G. And how do I compute that? It's easy. I know the y components of all my points. I plug that in here, and I ignore the x component and just take the y component. It's easy to compute this. I'll show you the answer. SG is there. It's not hard to do this calculation. Just put those vertices in and take the y component, and you're done. So it's quite easy to do. So these expressions are unwieldy. So let's introduce normalized weights. So our normalized weights will be Q1 up to Qk. And of course, they're going to sum up to 1, Q1 plus Q2 plus all the way up to Qk. This is equal to 1. And using normalized weights, then these expressions become a lot simpler. There we get rid of the denominators and a lot of the tedious writing. And you see why Jensen introduced those normalized weights. Okay, great. So we have that, and we also know that SP less than or equal to SG, that's our convex polygon, told us that. And so now we have Jensen's N-way inequality. And there it is in its full glory. Oh, let's make a big box. This is a very beautiful thing. It's just incredible. So this is N-way Jensen's. Okay, and this is so powerful, it will easily derive all of the other ones, like N-way MGM, N-way AmRMS, N-way, all that stuff is just an easy consequence of this. Now you just plug in the right functions and you get that. So I'm going to do one example of this, and you're going to do the rest. I'm going to do N-way MGM. So that's what I'm going to do. So my example, and then I'll give you a bunch of things for you to do. So my example will be f of x is minus log x. And I'm going to derive all the N-way stuff using this. Well, okay, let's get to work. I have my Jensen's inequality right here. And let's plug everything in. I get this. I put in minus log for the f's, and I get this. Now I'm going to do the same trick I did before. I'm going to multiply both sides by -1, but I have to reverse the inequality. There we have it. And now we can contract all of this stuff together. I'll show you. So that's log of A1 Q1 a2 q2 power q2 ak power qk, and this is less than or equal to the same thing. Now I removed the logs by taking exponential function of both sides. And I have my final result, which is this incredible formula. Would be pretty hard to prove, I think, by pure algebra and induction, but it was more or less effortless here. This is N-way. Well, I have K, but I keep calling it N-way. N-way Jensenized MGM. And you say, okay, how can I get the usual N-way MGM from this? Well, let's do it. Q1 is 1 over K, Q2 is 1 over K, and so on. And QK is 1 over K. And if I do that, I get A1 1 over K, A2 1 over K, AK power 1 over K less than or equal to, it's going to be A1 plus A2 plus plus AK all over K. And this is just kth root. Let's see if I can write this nice. Kth root A1, A2 up to AK. And this is arithmetic mean. So this is MGM. This is N-way MGM. I hope you see, and I hope you agree with me, and I hope you're convinced that convex polygon theorem is incredibly powerful because it allowed us to more or less effortlessly. It's not, I mean, there's effort involved, but it's really clear and logical. It flows very beautifully. You start with convex function, you draw a convex polygon, you take the vertices, and bang, you get all of these inequalities. So you can see that convex polygon theorem is very, very powerful. And now let me give you just a few exercises to do. I'm sure you can predict some of these exercises. Take f of x. F of x is x squared. That's a convex function. Apply the N-way Jensen inequality. You're going to get some generalized inequality. Okay, so you do that. And then you derive then the N-way RMS. Next one, same thing, same idea. You take this function here and you apply the N-way Jensens. You're going to get some huge monster N-way inequality. And then you derive the N-way arithmetic mean, harmonic mean inequality. So there you go. That's some work you can do. And I'm sure you can think of other things to do. Well, that's it. I hope you liked this. I think this was a really great application of some really good mathematics. You know, it's not just, high school math or college pre-cal math. This is like real math, and we saw where it goes, and it had amazing results. And I want to point out that this theorem of a convex polygon centroid and weighted mean, it seems really abstract. Some people will always ask you, yeah, but what are those things good for? Show me a real application for all this abstract stuff, something real world or whatever. Well, yeah, I mean, now you can see some real applications. I mean, all of these inequalities follow from that abstract principle of centroid of a convex polygon. And not only that, you wouldn't have all these machine learning algorithms or optimization, or none of that would work if that abstract principle wasn't true. Nothing would work in analysis either, because you need these inequalities in analysis. Well, so like and subscribe, and I'll continue to make more videos, and I will see you next time.